Our speaker this evening has 16 years developing algorithms in computer algebra. He's both a mathematician and a software architect at ArangoDB. Please give a great big round of applause. Welcome to Dr. Max Neunhoeffer.
Thank you very much. It's actually the first time that I'm giving a talk in a stand-up comedy club. I'm a bit nervous. Usually I'm not that nervous with talks, but on this occasion. But I hope that I can entertain you for an hour or so. If there's any question in between, just shout out and pose it. Yeah, many of the things on this slide have already been said. Originally, I'm a mathematician. It was just in 2013 that I wanted to change jobs and change countries and moved back from Scotland to Germany, where I was born. And before that, I was actually teaching at the university mathematics. And I was developing computer algebra software, and I was actually already then shuffling around with big data. In mathematics, we tend to want to compute things, and I was in the business of enumerating big things and computing group theoretic structures and so on. You probably don't want to know about that, but it was a lot of fun. And these days I help to develop ArangoDB. I actually do work on the kernel in C++, and I do software architecture, and I'm giving talks. So, the company I work for is called ArangoDB GmbH. That's German. And it is a spin-off of Triagons. And Triagons is a company which was founded in 2004 and has a lot of experience in specialized database design. So Triagons was essentially doing NoSQL databases before it was invented, before the word NoSQL was invented for these types of databases. And the experience comes from software architecture, from consulting, from business analysis, and from very, very particular needs. And essentially, around 2011-12, they figured that maybe one should create the one database which they wished to have had all those years. And that is how ArangoDB was born. It was actually started in 2012 as an open source project. It's on GitHub, you can download it. It has Apache 2 license. And it was only in 2014 that the company I'm currently working for, ArangoDB, was founded to take care of ArangoDB, do the development, and obviously offer services and service level agreements and training and all the rest of it. Because that's how we want to do business. So, what I want to do in this talk, I want to tell the story of this database, tell the motivation, why one could possibly want to develop yet another NoSQL database. And I want to start with a typical software project. Let's say a web shop. People sit together at the beginning, the business people, the developers, the managers, and they talk happily what they want to do. And it's all merry, and they say, well, we need an online shop, we need a recommendation engine, and we need statistics, and so on, and so on, and so on. It's all specified, and then the developers get to work. The database engineers, the coders, the front-end people, everybody works. They deal with relations, they deal with tables, normalization, schemas, you name it. This is a database meetup, so you all know these things. But when it comes to delivery, the situation is no longer that merry. At the handover, the managers say, this is not what I wanted to have. This is not how it should work. And somehow it all went wrong. So what has happened here? Why did this happen? Well, in the first part of the talk, I want to say a bit about this and how it probably can be avoided these days. So what do people do to try to not have these problems in software projects? What people do is they use more agile methods. So the development as such is done with lots of quick feedback, code sprints, Scrum, and so on. Rapid prototyping, such that the product evolves more quickly, and the stakeholders, the product owners, at all stages can look at what is there and can easily see early that things go wrong. And then, because you see it early, you can correct it, and you can change the design maybe, or change the front end or whatever, and can give continuous feedback to the developers. That is all fine. It promises less surprises, higher flexibility, and less problems, but still, not all problems are gone. And this brings me to the second big idea. And that's what Eric Evans described in 2004, the so-called domain-driven design. So what he says is that for such a project, one should identify a domain, that's somehow the situation where the software is applied, make a model of that domain, describe it theoretically, and use an ubiquitous language to talk about this. Ubiquitous means that all people in the team, from the developer to the front-end developers, to the managers, to the stakeholders, they must all speak the same language. Because a lot of the problems come from different languages spoken. And then one defines the context in which the model applies, and to be able to have this common language, what one has to do is to do the data modeling, that's what concerns us here, to do the data modeling as close to the domain as possible. So the domain is what is given from the outside, the situation where the software ought to run. And what you want to do to make this language possible is to be with the data model close to the domain. A good example for that is object-oriented programming. Yes?
This model, what kind of model do you have in mind here? Is it data model? Is it domain model?
This was
not data. Is it some processes?
Yeah, this is a domain model involving processes and entities and stuff and so on. I don't want to go into much detail, but it describes the domain in a theoretical way. Yeah. And the models I'm talking down here is the data models. Right, in object-oriented programming, your objects in your application are modeled by the reality. So there's an object representing something in reality. So the data is close to how things are in the domain. Now, if you look in a traditional system, a traditional method, then if you just listen to these people, the product managers, they will talk about the customers browsing through the shop. They will say we need a powerful search engine and the good items, whatever that is, should appear on top. And they want useful recommendations. And notice that at this stage, it seems to be clear what they mean to them. But what are the good products? Are those the ones the customer like? Or are those the ones where you can make a lot of profit? And it's highly likely, if you just talk about good, that this is not really understood by everybody. The developers, at least in the traditional relational world, they talk about really technical stuff. They talk about tables, normalization, queries and joins. They talk about secondary indexes, front-end pages and so on, and they have their buzzwords as well. And if you compare the terms, then you notice that the two different groups of people actually do not speak the same language. And a big reason for that is that the traditional approach with joins and tables and relational model makes it necessary that you translate quite a lot. And translating somehow means change language, and that is bad. And unfortunately, this in the end might lead to the fact that both groups, of course rightfully, think from their perspective that the others are morons. Yeah, the developers say, well, it wasn't obvious to me what the manager meant. And the managers say, how can these developers develop such a silly product which is not useful in practice at all? And I claim that the reason behind this is that they simply don't speak the same language. Yeah, they don't understand each other. Nobody is a moron here. So they don't speak the same language, they talk different things, mean different things with the same words, and have different words for the same things. And therefore, it leads that the functionality which is needed is actually not really methodically gathered. And things which are obvious for somebody are missing in the end. And there's a big misunderstanding, like in this famous project here. So, before we close the theoretical part of the talk, let me just give you a little bit of an idea what kind of language Evans could have meant. He talks about things like entities. An entity is something which has an identity. So it consists of data in a sense, but like a person, it has an identity. And if you change some data of the person, it's still the same person. This is in contrast to value objects, like for example an address. If you change an address in the slightest, well, then it's a different address. So this doesn't have an identity. So these are obviously two terms which do make sense in essentially all projects. And so therefore, a first step towards such a language is that one identifies the entities and values which occur in this domain. We can go on with aggregates. Aggregates are pieces of data where you combine value objects and entities. Typically, you say this is the data for an entity, and we put multiple values in their set. And you associate different entities and values. Yeah? That's an association is a relation. This can, for example, in the program be a pointer going from one object to another, or a reference, or whatever. And so you see, this is kind of, this is just here to give you an idea of the type of words which should occur in this ubiquitous language. So as a consequence of these ideas, what does this mean for the design? For the design, it means that those words which really come from the domain, these concepts, they must also be visible in the software design. If so much translation has happened, such that these things are no longer visible at all. For example, if you translate a relation where things point to each other, if you change this and press it into a table, then a lot of transformation has been done, and the original thing is really no longer present in your data model. So this all advocates that one makes sure that the whole team speaks the same language by at least adjusting the data model to the domain. And that's some kind of a long motivation for the next concept I want to introduce. And that is polyglot persistence. Another famous guy, Martin Fowler, didn't say it exactly like that, but I say what he meant, or what he should have meant is that. If you design a large system, you should cut it into parts, and you should use the right data model for each part. So for example, if you have an object or some kind of structured data, then you should probably store it, if you persist it on disk, you should store it as a JSON document. JSON, the JavaScript object notation. It's highly recursive. You can put value objects into one another. You can really model your data as you wish. And so that's a very good data model for, say, objects. If you have a hash table in your application, then if you want to persist it, you probably should use a key-value store. And if you have relations between your objects, pointers, references, then you probably should store them as they are, as a graph, as a mathematical graph, in a graph database. And if you have really a homogeneous array, if you have a table where all the rows are essentially the same format, then it's good to use a relational database. And if this table has many holes and is inhomogeneous, then you want to use a column-based database. And for all of these things, you of course want to take scalability into account. You want to see what part of your system has what scalability requirements. and then again choose the right data model. What Fowler originally said was, let's use the right database for the right part. But my point is that the really important thing is the data model. It's not to choose the right database, it's the right data model. Let me quickly run through some of these data models or engines you can have. Okay, this is a database meetup, so I should really be fast here. I want to mention essentially three. I know there are more, but here I want to mention three for a reason. The first I want to say is document stores. And if I say document here, then I mean JSON document. And a document store stores JSON data, and it has collections. So a collection consists of a set of documents. You can have multiple of these sets. And in particular, the database can inspect the objects because the values, it knows that they are documents, they are JSON. So for example, you can do secondary indexes. In essentially all cases, you have a primary key, so a unique key, to identify your documents, and you can have secondary indexes. Important is that even the documents in the same collection can vary in structure. So you can just throw arbitrary JSON data next to each other in the same collection. The database has to deal with that. There's no schema required, and so therefore you can just throw in whatever you want. At the same time, if you do a data design with a document store, you can relax your needs of data normalization. That's actually what people advocate. Sometimes it's better to embed certain data in a document, even if you have to copy it and keep it twice, because when you later access the document as a whole, you get all the data without having to do any kind of join or getting data from other places. Quite similar are key-value stores. They are essentially hash tables. But what you usually have there is that you have opaque values. So the database does not inspect the values. So in particular, it cannot do secondary indexes. What you gain is that you have extremely fast key lookup. You can specify the key and you get the value. So that's very high performance and very good scalability. But then the possible queries you can run are limited. A completely different breed of database are graph databases. Let me quickly say what a graph is. A mathematical graph is just a combinatorial structure where you have vertices, these are somehow dots somewhere, and you have edges, which are basically links from one vertex to another, or from a vertex to itself. Sometimes you have directed edges, sometimes you have undirected edges, and so all that matters for the graph is who is connected with whom, maybe in a directed way. And therefore, graphs are really a good model to model relations. The most famous one is, of course, the Facebook friendship graph, where the customers of Facebook would be the vertices, and there would be an edge from customer A to B if they are friends. Yeah? So these kinds of relations are very well modeled by graphs. In practice, graphs describe data very naturally, in particular in the presence of one-to-many or many-to-many relations. You can store graphs in tables. You just say, let's do a row for each vertex. I should say that usually you want to store some data with each vertex, and again, some other data with each edge. And so you can do this in tables by just saying, let's have a row in one table for each vertex, and some ID there, and then you have another table with all the edges, and there you store two columns, which say the edge goes from here to there. No problem storing that. But when it comes to graph queries, then you pay. Because what are the typical graph queries? Graph queries, questions about graphs are usually following the links, following the edges. So the question is, what is the shortest path from this vertex to that? And suddenly you have a very, very expensive multiple join because you don't know how long this path is in the first place. And so you have a kind of variable length join, or variable number of joins, and that's notoriously too expensive. So in a graph database, all this is taken care for because you have the typical graph algorithms like shortest path, or give me the neighborhood, or do some depth first traversal, or whatever. You have all this built into the graph database, and you can run such queries. Obviously, for this to make sense, you need a good query language which is adapted to this graph situation, where you can actually formulate easily the right questions you might have. One should be honest, with graph databases, horizontal scalability is troublesome. It's actually subject to current research in computer science, and to say that somebody has something which really scales horizontally with all interesting graph algorithms is usually a lie. I would say at this stage it's always a lie. Nevertheless, there are certain things you can do. For example, Google has come up with a framework called Pregel to do a kind of map-reduce for graphs. It's slightly different to what you usually do with MapReduce. In MapReduce, you usually have one map step and then a reduction. In that framework, for graphs, you have to do something else. You do a map on each node, and then you are allowed to pass messages along the edges of the graph. And since you don't know how far you want to go, typically, you have multiple routes. So this Pregel framework formalizes that and allows you to deploy very little code and run kind of interesting algorithms. For example, Google's PageRank algorithm is actually done in the Pregel framework, and as you know, it scales well. So there are algorithms which do scale well, but in general, if you just take your graph and distribute it all over the place, and run any kind of graph algorithm, then it usually will follow the links and hop around and lead to a lot of communications. And as you know, communications is usually a bad thing for performance. Anyway, that's your graph database. So, let's look at it. Here, there's one more comment I should make. Graph databases, there is many of them, but there's no good standard. So they vary widely, and well, everyone is different. So I know that there's more use cases and there's more data models. There's a columnar store, and then we talked about relational databases. But I've, for a reason, mentioned these three. And this we will see after this slide, in which I want to give you a typical use case. I've talked about Polyglot Persistence, and the idea was use the right data model for the right thing. So let's look at the typical things like an online shop, as we spoke before. You would have your customer data, and that's quite homogeneous, but sometimes not. For example, a company might have two different customers, say Google and myself. Probably you want to store more information about the customer Google than about the customer Max. And so even in this case, where it appears to be homogeneous, the data you store for each customer can be completely different. You have your product data, and depending on what business you do, again, you might have completely different data for that product and for this product. So that, the latest, is rather inhomogeneous. Every good online shop needs a shopping cart, typically displayed in the upper right corner of your screen. And that has to be displayed very quickly, because every single page you give out has a little icon with a shopping cart. And so, therefore, this needs fast lookup, but it's not that valuable data. If a customer loses his shopping cart, well, he has to shop again, but that's not a big deal. It's worse if you lose the data about a product. Order and sales data, that relates customers with products. So there's already sounding something like a graph, but typically you can still store this in tables, say. But then when it comes to building a recommendation engine, then you have somehow linked data. Yeah, you have this information, this customer bought these products, and this other customer bought this product as well. And so it's probably sensible if we recommend to him to buy these other products this other customer bought. And so what happens in the recommendation engine is that you follow links and you hop around your data and you gather data to learn what you could recommend to what customer. And if you look at such a system and decide for the software architecture what type of data store, what type of data model would you use, then if you do this from scratch now, then you would probably use something like MongoDB, a document store, to store your customer data. You would also use MongoDB to store the product data. When it comes to the shopping cart, you would say, here I need a key value store, something maybe like Redis, running just in memory. Order and sales data you could also stick in MongoDB as documents. But for the recommendation engine, you would probably deploy a graph database like Neo4j. So here you go. This is Polyglot Persistence. You have different persistence products for different parts of your system. And that's the original idea of Martin Fowler's. As a consequence, if you deploy such a system, you have to deploy multiple databases, multiple products in a single project. That is the original idea, but it causes some friction. Because you have to keep the data in sync. Sometimes you even have to copy data. You have to make sure that it's consistent. And even if this, in particular if this is different databases, you have to do data conversion. And you have problems like you need to change something, but then you have to do the change here and there at the same time. There is no such thing as a transaction spanning multiple databases. Yeah? And so you have a lot of problems. You have additional installation and administrative effort. And you have more training needs because you need to use more different products. And so my provocative question at this stage is, Polyglot persistence is a good idea. So wouldn't it be nice if we could use this idea and the benefits of it, really high performance and easy programming in all parts of the system, without paying with these disadvantages? That would be nice, isn't it? And now we come towards the part where there's the sales pitch. And after all, I'm working for a company, and we want to sell our product in the sense that you do not pay for the product, but that you use the product and eventually maybe pay for the services. The new idea here is the so-called multimodel approach. So what is a multimodel database? And that's actually what my colleagues in the company came up with, say in 2010 to 2011, the thing they wish to have, and at the same time that can be built. A multimodal database combines a document store with a graph database and a key value store. So in a sense, it is a document store, and it stores the vertices and edges of the graph you want to store, in the sense that it puts the vertices in a vertex collection or in multiple vertex collection if you need, and it stores the edges in an edge collection. So in that sense, it's no different than what I described with tables storing graphs. But since it ought to be a graph database as well, what we want is that we have in such a thing a common language to do queries for all three data models. Yes?
Quick question. Essentially, vertices and edges you put instead of graph database, you put in document the store.
Yes.
Effectively, this is what
for the storage, what you do is you store your graph in the documents.
Yes, exactly.
And since you want to store data with each vertex and each edge anyway, that's probably not a bad idea. But then you must make sure that all these graph querying facilities, all the graph algorithms a graph database has to do, that they are actually present in your database as well.
They implemented there, but
exactly.
effectively it's the same way again, I'm not offering now to do this, just theoretically. You could put the same graph, whatever you store in graph database, you could put in a relational database. You can put it there. Whether performance and so on good or bad, it's another important question.
Exactly.
But you can. Why not?
Yeah. The problem is, if you do that, then you probably get the good old problem of multiple joins,
Yes.
which is a performance problem.
Yeah, this is exactly what I had in mind.
So therefore, it's probably better to follow this more flexible document approach. The key idea here is that such a beast, combining these three, can actually compete with specialized products successfully. Why is that? Well, it is a document store. And just because you have added some graph features, this doesn't mean that as a document store it is less performant. And it is a graph database, as we just spoke. This is a sensible way to implement a graph database. So there's no reason why this thing should be slower or less performant than a specialized graph database. With key value stores, well, a document store is a key value store. You only have to make sure that if you just use it as a key value store, delivering values which are JSON, that if you do choose not to have secondary indexes, then it must not be slowed down. So again, for a key value store, it can compete with specialized solutions. And therefore, what it offers for you is that you have this idea of polyglot persistence, but suddenly you need only a single database. Because you have these three data models all in one product. And what's more, you can not only use it as a special player in each of these areas, what is even better is that in a query you can mix the data models. So you can do things like, give me some documents from this document collection. Now, from each of them, follow the links in the graph a few steps, maybe until you find something, and then take all the results and join them with some other connection, say.
But you need language for that.
Exactly. You need a language which can do all this. Yeah? And if you are a bit clever, then you can actually replace, in many cases, a relational system with this as well. Because, after all, you can just take every row of the table you want to store and stick it as a document in your document store. So you only have to make sure that the database recognizes automatically that suddenly all your documents have the same structure, the same shape, and that they are then stored efficiently. And suddenly, you can essentially do what a relational system can do as well. So we'd like to depict this situation with this map here. So this is an attempt to sketch the NoSQL database world. Let me just say a few words to this map. You have two sides. On the left-hand side, we have depicted the operational database things. These are database engines which essentially deal with mutable data and process transactions with low latency. That's what you need in the operational business. On the right-hand side, you see the analytic side. In the analytic world, you basically deal with large sets of immutable data, and all you want to do is somehow find out something about this data. Do some aggregation or do some MapReduce and analyze it. And obviously, you need totally different technologies for that. That's why we have distinguished that. Then, of course, on the left-hand side, in the operational world, which we have intentionally drawn larger, because in many projects, you have only an operational side and no analytic side, and there are very few projects where you have only analytic side. So what you see here is the document stores, the key value pairs, and graphs here. So here in this area, you see the data model side. But there's more. For example, in the north, you have complex queries. So that's now not a data model aspect. It's an aspect of how you use your data, what you do with it. Likewise, here is another property of a database, namely to be extensible. Yeah? And down here, you have something about scalability. So here's the massively distributed area, which is well, close to key value, because essentially if you really want to massively scale, then you have to be close to a key value store. And we have distributed the main players over here. MongoDB would sit in the middle. Redis is here, maybe. And Riak is here, distributed key value store. Neo4j, of course, here. And over in the analytic world, I have put Hadoop. And okay, obviously I missed some out, but I think you get the idea. I'll come to this map in a second. So now let me introduce what we want to do with ArangoDB. As I told you, this project was started only in 2012, but with a lot of experience with database technology and actually with NoSQL database technology. And the project is from day one on to make a multimodal database. To take intentionally these three data models, graph, document, and key value, and put it into a single object, into a single project. It is open source and free, as essentially all NoSQL solutions are. It has the very free Apache 2 license, so you can essentially do anything with it without paying. It offers convenient queries. We have this AQL query language, which you have already shouted out earlier. And the essential API is via HTTP REST. Therefore, it is relatively easy to write database drivers for nearly all languages. And the queries are actually quite powerful. For example, they can do joins. Yeah, so there's no reason, essentially, why you shouldn't be able to do joins like in the relational world, now just between different collections. Obviously, not every type of join can scale, but some can, and therefore it's not a good argument to say some joins are slow, so therefore we don't do joins. Rather, you should do joins when you can efficiently distribute them, and otherwise do something else. We do strong consistency guarantees because you do have transactions, and we believe that this is important. One shouldn't ignore decades of research in the relational world. ArangoDB is quite memory efficient, so it looks at the documents and recognizes their shape, and actually recognizes similar shapes of different documents in the same collection, and therefore can actually, in many cases, replace a relational database. The database kernel is developed in C++ for efficiency, and we embed Google's V8 JavaScript engine and implement quite a lot of the higher level API of the database in JavaScript, which is executed in the server with direct access to the data. You can even extend the API with your own JavaScript code, which you deploy to the server, and we have a framework for that, which is called Fox, thus these little animals we have thrown around. There's many drivers for different languages. Obviously, we want to have many users, and there's good documentation, a web frontend, which I'm happy to show later. And there's good community support and professional support by our company. So coming back to this map here, what is the target area we somehow dream of? Well, we figure that what I have drawn green here is the area where we have the key competency of our database. So these are the things, these are the places on this map where we can compete with specialized products successfully. So we are a document store, we are a graph database, and we are a key value store. And if you compare us to specialized solutions in these areas, then we should come well out. We offer complex queries, and we are an extensible database. So therefore, we cover all this green area. That's not to say that we don't cover the white area. But in the massively distributed and in the analytic world, it is clear that just by software architecture principles, specialized solutions will be better. Yeah, because you can't do all. But I think the amazing idea is that the three things, documents, graphs, and key values, you actually can do all successfully. And you can combine it with transactions and joins. Right, I want to cover a few of these aspects in a bit more detail. The first is strong consistency. If you look at your standard document store, then it will offer you CRUD operations for single documents. That is fully ACID, atomic, isolated operations for single documents. Well, there's not much you can do apart from this. But we believe you need transactions spanning multiple documents and multiple collections. Think, for example, of a graph in the way we store it. If you want to remove a vertex, then surely you want to remove all the edges leaving that vertex and arriving at that vertex at the same time. And there's no point that any other transaction sees this operation done half. So even there, you have multiple documents, multiple collections, and you want to have transactions for that. In the same way as you want to have transactions between different tables in the relational world and transactions with different rows. For reading complex queries, you have snapshot semantics. That is, the query sees the state of the database in a particular point of time. And we have very secure, durable storage because we do append only and we keep multiple revisions, as many as are needed. All this works for documents as well as for graphs. After all, your graphs are just consisting of documents. In the near future, we will extend these strong ACID semantics even for the cluster situation, for the sharding situation. We are not quite there yet because we have to implement MVCC semantics and log-free operation for all the indexes still. That's on the roadmap. It will be done early next year. And then we will really have the full ACID semantics in the cluster. We believe in this strong consistency because it simplifies application development. If you have less consistency guarantees, then you have to solve the corresponding problems in your application layer, which complicates things. Sure, in many cases, or in some cases, you want this. You want eventual consistency. Well, but then you get it because you can do, as I will say in a second, you can do, for example, asynchronous replication, and you can not use the transactions, and you get higher performance and eventual consistency. With respect to replication and sharding, we offer horizontal scalability essentially at this stage in two ways. The first is you can really easily set up asynchronous replication. So you don't have to change anything in your database server. You can just attach asynchronous replicas by telling them, well, attach yourself. And this gives you very good read parallelization with eventual consistency, because you can just write to the master, and then very soon all the replicas will have the data, and you can just parallelize your reads on all these slaves. We do have sharding, and the data distribution is automatic. So you just say, I want that many servers, and a collection spanning that many shards, and the data distribution is done automatically. Obviously, what you need for that is fault tolerance and automatic failover. And again, that's scheduled for very soon in the new year. Because if you run a cluster with 100 machines, then surely after a few weeks, one of them will fail. So you need automatic failover. And we will do this with zero administration. That is, it will essentially repair itself, and the data will rebalance itself if you add or remove nodes. And all of this needs to be done. And again, we are very busy implementing all these things, but it can be used now. Let me say a few words about the query language, and I'm happy to show you some examples of that later. It allows complex queries. You can do transactions and joins, and you can even extend the functionality of the query language with your own JavaScript code. Yes?
Yeah, just you have developed a cluster class database. You still have strong consistency currently?
Yes, so as I said, you can do transactions right now, but they are not fully isolated at this stage. But early next year, we will have the strong consistency and ACID guarantees even in the cluster. Yeah, and also the transaction semantics, because we use multi-version revision control. So all this works in the cluster as well. And the AQL language is actually independent from the language driver you use, because it's a string which you send to the database, which we in the database server parse and analyze and optimize. And so therefore you would have to use the same query if you have multiple clients, maybe even written in multiple programming languages. And just a minor thing, we have the infamous SQL injection. The language has some design features against that. And of course your question goes into that direction. What about the cluster? Yeah? We actually had to re-implement the whole AQL engine for the version which we published just now. So the beta release is out. So we have re-implemented the query optimizer and query engine in C++ for higher performance, because we noticed that the old implementation, which just translated to JavaScript, wasn't up to global optimization. What you need to do for such a query language and for cluster operation, you need to produce a cluster execution plan and have some instance of an optimizer. Think about this plan and think about what kind of filtering and sorting can we do distributed and how can we combine the results and so on. And we needed this kind of optimization. And that is done here. There's a query plan made describing the global situation of the cluster. It's optimized with distribution in mind. And then it is cut into pieces and deployed to all the servers in the cluster. And links are made with HTTP requests. And then it's executed. And this allows us to give good performance in many cases, and still reasonable performance even if it's difficult. Yes?
Yeah, this is very interesting. Is there a design document or a white paper that describes how this works?
There will be one shortly. We have literally released the beta version of this optimizer last week, and the actual version 2.3 is supposed to be published at the end of the week. I'm jetting through the world and giving talks, but when I'm back I have to write exactly that. Yeah? And yeah, I'm giving talks on this, and I'm explaining this, and I will write a white paper. And at this stage, you just have to look at the source code, which is all there.
Is it open source?
It is completely open source. You can download everything I do every day and look at it. And you can use it for free. Final slide. The database is extensible. I've already told you that we embed V8, the JavaScript engine, in the server. It runs very rapidly and it has direct access to the data. And there's a framework called Fox, which allows you to have user-defined API extensions and implement further URLs of your database server. So you can essentially implement your own database services, which can use the full power of AQL and transactions and direct access to the data and cluster, and can extend and tailor the database in exactly the same way as you need it. That's in particular important if you have multiple devices and clients, and you can do a design where you do whatever is needed as your business logic close to the data, and have the services which need to be there executed quickly, and you can have your favorite framework for applications before that, and you don't have to copy too many things as in the client code. People say that this is a security risk to execute code in the database, but we believe that it really increases security, because since you are close to the data, and since you can tailor the API of your database, this means that you can implement your own authorization and authentication scheme on a document level basis. And you can then switch off the main API of the database and really only expose exactly that service you need. And for example, if you are into schemas, I said initially that you don't have to have a schema. You can really rapidly start and just throw whatever JSON documents you want in there. If you later, obviously will have a schema in your mind, if you later want to enforce this, you can actually do the API which enforces whatever schema you want to have and whatever consistency you need through the API extension. And since JavaScript runs everywhere, surely you have to use it in the browser. Here you can use it in the backend as well. You have just one language everywhere. For example, if you use Node, but then you could have another framework like Ruby or Rails in between and have a second language. That's all up to you. This comes down that you can do this microservice-oriented architecture with this database, with the advantage that you have to deploy only one database and can use it in different parts, or have all your data in the same database and enjoy the benefit that data is close to itself. Right, that's why I want to stop. Thanks for your attention. And obviously we will have questions and answers. And I'm absolutely happy to present some things live on stage with the database, should you ask me.
Okay, before we continue, I just want to give a great big round of applause to Dr. Matt. First question of the evening. Hands? Right there.
Is there any performance benchmarks on it compared to other NoSQL solutions?
We have some. They are a bit dated, so we intend to do this anew. But we, of course, we have to compare that. I'm not aware of one published with a graph database, but that ought to be done soon. We're so busy developing things that we didn't get around to, but I think our benchmarks will be comparable.
Yeah, you said on your online shop that you can use this database for how accurate is your browsing history from your online shop, based on the keywords that customers would use.
So we are not running an online shop. It's just a use case which is typical. And other companies are using ArangoDB, but I wouldn't know the details of what they do. Yeah.
Anybody using the production environment now?
Yes, it's starting. We are still a young product, and we are over in Germany. So this is essentially the first or second trip to the US to do advertisements and so on, and to talk to people. We have a bunch of users in Germany. We don't have the Googles and Amazons of this world so far, but we have users, and the users which we get are getting bigger, and we have already questions for service level agreements and so on. We haven't sold many, but it's still so young and developing so rapidly, and with database technology, people trust the old solutions more than the new. But we are gaining ground, and we have customers who are using it. If you go to our webpage, you see the logos.
You're waiting. Yeah, is reputation your high availability option?
Sorry, I didn't get this.
What are your options for high availability?
High availability. At this stage, you can have a cluster, and already now the system is as follows. You have so-called coordinators, which just take the queries, and you have in the back you have database servers. And what happens? You talk to the coordinators, and they talk to the database servers. The coordinators are stateless, and you can run as many as you want. And if one dies, you just use another one. So there we have complete failover, and it's no problem whatsoever. In the database backend, this is one of the next steps of our implementation strategy on the roadmap. So what we will do in the first instance is that we pair the servers. So there will always be two, and they will do synchronous replication. And the coordinators essentially talk to both of them, and both of them have to confirm until the client is informed. And then there is some background mechanism which detects if one of them fails, and that's automatically taken out, and the other takes over. So that's the plan for the first step. And later on, we will have more complicated distributed failover, such that you have a solution where you can shoot down any of your servers, and the others automatically take over because they are replicas, synchronous replicas, And you just get an email in the morning in your own time. You go there and fix it and plug it in, and it will pass automatically. So that's the dream which we will achieve sometime in the middle of the next year.
So in terms of CP theorem, you are like on C and P side.
Exactly.
Your availability will be
Yes.
someone in the future.
Yes.
Okay.
What about shortage? Do you provide hash-based or range-based shortage?
So far we have only hash-based, but you can configure it exactly to which attributes you want to use. That's in particular important if you have a graph. You really want to make sure that the vertex collection is sharded in a way, and the edge collection such that the outgoing edges, say, from your graph are on the same machine as the vertex. So you can configure that. And in the future we will have range-based, but that's not yet implemented.
Okay. And what about the compaction? Because since you use MVC up and down the data, right?
Yeah.
So what about compaction? We have to remove the deleted, for example, I deleted a document.
Yeah.
I have to remove the document from the physical storage. So what kind of compaction do you guys do?
Okay, I could give you a talk of another hour about this, but in 2 sentences, we have a write-ahead log, and for all collections, everything the database writes is written to the write-ahead log first. Then there is something called the collector thread, which reads the beginning of the write-ahead log, if no transaction can see this anymore, and distributes the data to the data files, again only appending. And then for the data files, we again have something which we call the compactor. And again later, when it's time, it recognizes if many documents have been replaced or deleted, which are no longer needed by any transaction, and then it will, in its own time, copy over the documents from one data file to another, and thereby compacting it. It's all quite complicated, but it works very well, because we are a complicated multi-threaded system, and great care is needed to get this right.
Yes.
I'm kind of curious about transactions in a distributed system and how you do that, because a lot of what you are, this is very similar to Mongo in some ways, but that's clearly something that Mongo doesn't support.
Yeah.
And it seems kind of like a bit of magic, right? It seems like
Yes.
a nice achievement to be able to do that.
Yes. So what happens is that at first glance, the coordinator, where the query comes in, coordinates the transaction. So it keeps track what it did, and then if things go wrong or there's an abort, then everything is rolled back. But that's of course no good in the case of failover, because said coordinator might die. So the first, and to be honest, it's not full.
Coordinator's cluster level, that's not per.
Yeah, I know. This is not fully implemented. And the reason this is not yet fully implemented, the design is there, but the implementation is not yet there. Because unfortunately at this stage, our indexes only store the latest revision. So therefore, we cannot have an access for a transaction, because what is it a transaction ought to see? Well, each transaction has a start time, and what it ought to see is the result of every transaction which was completed before that start time, and no results of any collection which has begun after that start time. And that is what we need. We need to be able to look into the past by looking into the indexes. And that is what we do later this year. We make our indexes fit for this MVCC, and the moment we can do this, we can happily run a transaction without any kind of logs, even in the cluster, and it will exactly see what it ought to see, because we just keep the old revisions of the documents. And then we have concurrent operation. The only thing which is needed, and that is where it becomes difficult, and with the scalability, is we need some kind of centralized place where the transactions which are going on are kept. And that will be yet another sharded collection, and transactions will be described by documents. And of course, you need a very clever caching technique that you don't have to have many requests to that thing. But we are confident that in many use cases, this can be done really efficiently. We only need to sort out this MVCC problem with the indexes, and then have another look April next year, and It will be done. It's not easy, but it will be done.
And how much slower is that than, say, operations on a single collection?
Almost certainly it will be a bit slower, but then it's your choice. Either you want to have the high consistency guarantees and less effort into application at the cost that it is a bit slower, but not catastrophically so. Or you just don't do transactions and you do single document operations, and then it's perfectly scalable. So we want that the choice of this is yours. We don't want to make this choice for you. We want to offer you all the possibilities.
Next question? We have time for just one more. Yes.
Can you describe a little bit more about the Fox framework and specifically how it integrates with other development tools or visualization tools?
Yes. First of all, we tend to build our drivers in 2 layers. So for example, the Ruby driver comes in 2 layers, and the JavaScript driver will very soon be in 2 layers. The lower layer is a simple API to talk to the database. Yeah? And the higher layer will be a certain abstraction having all these concepts from the visualization frameworks like models and repositories and views and so on. And the Fox framework addresses both. Yeah? On the lower level, it lets you define new routes with your own database services which are implemented in JavaScript. On the higher levels, it has, again, models and repositories such that you can exactly attach the back-end services to the higher levels of your driver and to the abstract concepts in your visualization tools. Yeah, so it's all built to model exactly that. Does this answer your question?
Basically, yes. Yeah.
Good.
Okay, Dr. Max will be here for one-on-one questions. So anyone who get a chance, feel free to come on and up and talk to him. He will be right outside there, and I'd like to thank you all for coming. Thank you.
Thank you.